All right, welcome. Today, we're going to peel back the curtain on the invisible rules that power pretty much everything in our lives. I mean, from the outlet in your wall all the way to the phone in your hand, it's all running on a very specific set of laws. And you know what our guide is for this whole thing? A university electrical engineering lab manual. Yep, let's get into it. So you look at a board like this, right? An electronics trainer kit. It looks absolutely wild. So many knobs, wires, little components. But here's the secret. The thing they don't tell you right away. All of this complexity, it's built on just a few super simple, really elegant rules. So let's cut through all that noise and find those simple rules hiding right there in front of us. Okay, so before we can understand the story, we've got to learn the language. And the alphabet of electricity is actually pretty straightforward. It all boils down to just three key concepts, three letters that are the foundation for, well, everything. First up, you've got voltage. This is the push. It's the electrical pressure in the system. The absolute best way to picture it is like water pressure in a hose. The more voltage you have, the stronger that push is, forcing the electricity to move. It's all about potential. Next, we have current. Now, if voltage is the pressure, current is the actual flow. Let's stick with our water hose analogy. Current is how much water is actually moving past a certain point. It's the electricity on the move, and we measure it in amps, or just amps. And the third letter in our alphabet is resistance. Just like the name sounds, it's anything that pushes back against that flow of current. In our water pipe, this would be like a kink in the hose or maybe a narrow nozzle at the end. Every single thing in a circuit has resistance, and engineers actually use it as a tool to control exactly where and how much current flows. So here's the really cool part. Voltage, current, and resistance, they aren't just three separate ideas. They're locked together in this perfect little mathematical dance. This table shows it all. If you know any two of them, you can always figure out the third. This simple, totally predictable relationship is what makes electrical engineering even possible. Okay, so we've got our alphabet, V, I, and R. Now it's time to learn the grammar, the core rules that tell us how these things actually behave together in a circuit. Think of these as the non-negotiable laws of the electrical universe. And the number one most important piece of grammar is Ohm's law. It's so simple but so powerful. All it says is the more pressure you apply, that's voltage, the more flow you're going to get, that's the current. It's this beautiful direct relationship, and it is the absolute bedrock of basically every circuit ever made. And here's what it looks like when you actually test it. The lab manual shows a little circuit on the left, and the graph on the right, that's what happens. Look at that. As you turn up the voltage, the current goes up in a perfectly straight line. That right there, that solid predictability is everything. Building on that, we've got two more rules from a guy named Kirchhoff, and they're really just common sense. The first one, on the left, is about intersections. It just says that whatever current flows into a point has to flow back out. Electricity can't just disappear. The second one, on the right, is about loops. It says that if you follow a complete circuit, all the energy you start with from the battery gets used up by all the parts. You always end up back where you started, at zero. So, those laws are great for simple circuits. But what happens when you've got, say, a computer chip with billions of components? You can't analyze them one by one. It's impossible. So to handle that kind of complexity, engineers came up with some really clever shortcuts, theorems that let us simplify these huge, messy problems. One of the most powerful shortcuts is the superposition theorem. It's basically a classic divide and conquer move. If you've got a circuit with, let's say, two different power sources fighting each other, it lets you just pretend only one is on, solve the circuit, then do the exact same thing for the second one. And at the end, you just add your two simple answers together. Brilliant. It works just like this. Step 1, you calculate the current pretending the second power source isn't even there. Easy enough. Then, step 2, you do the opposite. Bring back the second source and pretend the first one is gone. And for the grand finale, you just add those two results up. It turns one super hard problem into two much easier ones. And this whole simplification thing gets even wilder. There's another tool called Thevenin's theorem that lets engineers take a massive, tangled up section of a circuit and replace the whole thing with something ridiculously simple. Just one voltage source and one resistor. It really is like a magic trick for taming complexity. Now, everything we've talked about so far, that's the foundation of basic electricity. But to get to modern electronics, the smart stuff, we need one more ingredient. We need parts that don't just get in the way of electricity, but can actually control it in clever ways. And this slide shows the crucial difference. On one side, you have passive components, like resistors. They just sit there and consume energy. But on the other side, you have active components, like transistors. These are the game changers. They can act like tiny, super fast switches or even amplifiers. This ability to control the flow, that's the jump from raw power to smart electronics. You know, the simplest one of these smart components is the diode. Its job is incredibly basic, but it's absolutely fundamental. A diode is a one-way street for electricity. That's it. Current can zip through one way, no problem, but if it tries to turn around and come back, nope, blocked. That simple little rule changes everything. So, we have our alphabet, we have our grammar, and now we have our game-changing smart components. Let's put it all together and see how this system pulls off a little piece of everyday magic, charging your phone. So here's the puzzle. The power coming out of your wall socket is alternating current, AC. It's constantly flipping directions back and forth, but your phone's battery, it needs a smooth, steady, one-way flow of direct current, DC. So how in the world does that little white cube that plugs into the wall make that switch? Well, step 1 uses our new friend, the diode. By putting just one of those one-way valves in the circuit, it acts like a bouncer. It lets the positive part of the wave through, but when the wave tries to go negative, it blocks it completely. So now we've got DC, but look at it. It's bumpy, it's inefficient, and we're literally throwing away half the power from the wall. Not great. This is where engineers got clever. Using a smart arrangement of diodes, they built a circuit that doesn't just block the negative part of the wave. It actually grabs it and flips it upside down, making it positive. This is called a full-wave rectifier. Now we're using all the power, which is great, but it's still this bumpy, pulsing current. We're closer, but this would still be terrible for a phone. And here it is, the final beautiful trick. We add one last simple component, a capacitor. You can think of it like a tiny, super fast charging battery. It charges up on the peaks of those pulses, and then when the pulse dips down, the capacitor releases its energy to fill in the gap. And the result? The bumpy mess on the left gets transformed into the smooth, steady DC voltage on the right. That's the good stuff your phone needs. And that's the whole show. First, you rectify the AC into pulsing DC. Then you filter those pulses to smooth them out. That exact two-step process is the magic that's happening inside pretty much every charger and power supply you've ever owned, all built from those simple rules we just went through. So there you have it. We went from the absolute basics of electricity, through its fundamental grammar, and all the way to the charger that's probably sitting right next to you. It kind of makes you wonder, right? What other pieces of everyday magic that we just take for granted are really just a few simple rules put together with a little bit of cleverness?